So in this set of notes, we're going to solve equations with variables on both sides, but we're going to encounter some special cases. We're going to see equations where we might encounter one solution, which is what we've been seeing, no solution, or an infinite number of solutions. So remember, a solution is the value of the variable that makes the equation true when you plug it in. Now, the directions solve really mean tell me what the variable can be. But mathematicians are efficient, so rather than say, tell me what the variable can be, they just say solve. So when you're solving this equation, and I say solve, I'm really saying, tell me what the variable can be, so that way if I multiply it times 3 and add 1, I would get 10. You go through your process of solving, of simplifying and then isolating. And to do that, you would first minus 1 from both sides, get 3x equals 9, then divide both sides by 3 to get a solution of x equals 3, which according to our solution, our definition, we know is going to be true because 3 times x, which is 3, is 9 plus 1 is 10. But when you give this answer, you're really responding to this command by saying x can be 3. So again, when we say solve, we're really asking for what the variable can be. And when you give your answer like this, you're really saying that x can be 3 and nothing else, which again is our expected behavior with a linear equation. We're expecting that all of our solutions, all of our equations are going to have one solution. So recall these steps here when we're solving with especially the variables on both sides. We're first going to simplify, distribute, or combine. Then we're going to balance our variables, and then we're going to balance our numbers. So here's our first example with variables on both sides. 3 plus 2x equals x plus 5. So to solve this, I would first subtract x from both sides. So minus x, because remember I can move my variable terms by addition or subtraction only. And the reason this would work is because x minus x is 0. So this would leave me with my new equation, 3 plus 1x equals 5. Then I would subtract 3 from both sides, bring down my equal sign 2, and remember that 1x is the same as x. And so my one solution to this equation is that x could equal 2. And so remember, if you're on the math game show, that means you get to come down and open door number 2. You're opening one door, but it happens to be door number 2. Here's a visual example of that same setup. So I've got my 3 plus 2x. So if I use these rectangles to represent an x, on my left side I have 2 of them. And then I have 3 single squares. So this is 3 plus 2x. And on my right side I have x plus 5. Now, a way to kind of solve this visually rather than algebraically might be to think about picking apples off an apple tree. So think of this like an apple tree and think of this like an apple tree. If you pick any type of fruit, or better, not an apple tree, but a fruit tree, if you pick any fruit off of this tree, then you need to pick the same number of fruit off of this tree. So what I could do is I could pick off these 3 single green squares from the left side, kind of get rid of them, but then I'd have to pick off 3 single green squares on this side, because remember, whatever we do to one side we have to do the other, so we're keeping it balanced. And then what I could also do is, so on this side I've got 2 green squares left, but I don't have any left to pick off on this side. And then on this side, since I have one rectangle that I could take off of each side of my tree, I could take off one of these. And so what I'm left with is one rectangle, which is my x, equaling 2 green squares, which equates to my solution of x equals 2. So this is just kind of a visual representation of the algebraic equation solving that we just showed. So now let's see some of our special cases examples. So for equation A, I have x plus 1 equals x plus 2. So on the left side of my scale, I've got one rectangle representing x and one green square. On the other side, I've got one rectangle representing x and two green squares. So if I were to try to balance this similar to what I did before, what I would do is I could remove one of my green squares from each side, so pick off one piece of fruit, and then I could also remove the rectangle. And so what you'll see is that on my left side of my balance scale, I'm actually left with nothing, which means I'm left with 0. And on the right side of my balance scale, I'm left with 1. So imagine that at a balance scale, if one side were 0 and one side were 1, could that scale ever be balanced? You could take it a step further, and you could think about it this way. Let's go back to before we took the fruit off the tree. If this rectangle represents an x and this rectangle represents an x, and these each represent singles, now imagine we made up a number for x. Let's say x equaled 5. Then this side would be 5 plus 1, which would be 6, and this side would be 5 plus 2, which would be 7. If on one side of my scale I start with the same number, the same x value, but on one side I add 1 and on the other side I add 2, could these two sides of the scale ever be balanced? No. There's no x value that would ever make this scale be balanced. That's kind of interesting. Now in equation B, I've got a similar kind of situation. So on the left side I've got 2 x's and 6 singles. And on the right side I've got a group of an x plus 3, but I've got that twice. So I've got 2 of those. And so again, I can think about it as if I were picking fruit off of the tree. So I could start by picking off 6 of these singles, and I'm able to pick off 6 on the other side as well. Remember, when you're solving an equation, whatever you do on one side, you have to do on the other. So if I can't do it on both sides, I can't do it. And then I can also take off one of these x's, but I can also take off the other x. So if I'm removing all of this from the tree, then what I'd be left with is 0 equals 0. Would that scale be balanced if there was a 0 on each side of it? And yes, there would. Now we can even take this a step further. I can go back to before I took the fruit off the tree. And remember that my rectangles each represent some unknown number that we're calling x. So I could put an x in each of these spots. And then each of my green squares represents a single, 1. And so I can see that on the left side of my scale, whatever x is, I've got 2 of them. And then I've got 6 more singles. And on the right side of my scale, whatever x is, so let's say x was 5 over here, then these x's would also be 5 because x is the same variable. So I've got 2 x's as well, and then 6 additional singles. So no matter what my x value is, my scales are always going to be even because I always have 2 of them and then an additional 6. So here, my scale can never be balanced, and here, my scale will always be balanced. So this is kind of unexpected. We're used to seeing one solution. Now we're seeing cases where we have no solutions, which means there's no possible values for x, or all real numbers, which means anything that we want x to be could be the case. And so which scale do you think is which? Take a moment to think about it. So the balance scale on the left is going to be no solution because there's no possible number I could pick for x that would ever make my scale balanced. And my right balance scale will be all real numbers because no matter what I pick for x, it will always be balanced. Let's go back up here for a second and solve these now algebraically. So if I were going to solve this equation algebraically, I can't distribute or combine, so I would start by subtracting x because x minus x is 0, but then whatever I do to one side, I have to do the other. So I'd subtract x from this side as well. Now if x minus x is 0 over here, then x minus x is 0 over here as well. And so I'd be left with 1 equals 2. Now if I tell you to solve and your response is 1 equals 2, I'm not going to be sure what you mean about x. And so what we're going to say in this situation is we're going to say no solution. So what we can see is that our variables have disappeared and I have two numbers that are not equal. Now if I go back to my visual just for a second, all I've done so far is I've taken the x away from both sides. So I've removed it here and here. And so you can see I've got a 1 equaling 2, which is not true and not balanced, so I've got no solution. Now in equation B, if I were to solve this algebraically, I would distribute first because I'm able to do so. I'm just going to do this off to the side. And so I would get 2x plus 6. I have no combining, but my next step would be to minus 2x because 2x minus 2x is 0. And whatever I do to one side, I have to do the other. And so after doing that, I would get 6 equals 6. Now visually, what I did on the balance scale is I removed both x's. So I could remove this x and remove this x. Whatever I do to one side, I have to do the other. And you can see that on the left side of my balance scale, I have the 6 remaining and also the 6 remaining. Those two numbers are equal, and so I can see it doesn't matter what x is. I'm always going to have all real numbers. So in both cases, what's similar about them is that the variable has disappeared, but in no solution, the two numbers that I'm left with are not equal, while in all real numbers, the two numbers that I'm left with are equal. Let's just put this into some definitions down here. So one solution is going to be when you do get x isolated, because that's always what you're trying to do anyway, and you get a number. So for example, if you get x equals 3 when you're isolating, this means that x can only be 3. Which means on the game show, you would get to open one door, and that happens to be door number 3. Now if you get no solutions, when you're trying to solve, your variable is going to disappear, and you're going to get a false statement. False statement when the variable disappears. And an example of a false statement would be like 7 equals 8. So if we get something like that, 7 equals 8, then the answer that we're going to put on paper is no solution. And what this means about x is there's no possible number that x can be. So if there's no possible number that x can be, this would mean that we get to open no doors on the game show. Or we can also have all real numbers, which would be when we get a true statement, when the variable disappears. And an example of a true statement would be maybe something like 9 equals 9. So to either have no solution or all real numbers, our variable needs to disappear. For no solution, we're going to get a false statement, and for all real numbers, we're going to get a true statement. And if you were on the game show and your answer is all real numbers, then this would mean that you get to open all of the doors. So at this point, I'm going to ask you to pause the video, try examples 3 and 4, solving them algebraically, similar to what we did up here. And then look at what you get. Does your variable get isolated, or does your variable disappear? And if so, be sure to either say no solution or all real numbers. Pause the video, press play when you're ready to check your answer. So in example 3, I started by distributing, and my new equation was 3x equals 3x plus 12. I then balanced my variables by subtracting 3x from both sides. 3x minus 3x is 0, leaving 12 by itself on the right side of my equal sign. Notice my equal sign didn't move. On the left side, 3x minus 3x is also 0. If 3x minus 3x over here is 0, it's also 0 over here. Now my variable disappeared, and so that means I'm either going to have no solution or all real numbers, but since 0 and 12 are not equal, that means no solution, which means there's no value of x that could ever make this equation true. Which also makes sense because here I have 3 x's and here I also have 3 x's, but on one side of my scale I'm adding 12 and on the other side of my scale I'm not. So this would never be possible to balance. On example 4, I also begin by distributing. So my new equation is 2x plus 10 equals 2x plus 10. I then balance my variables by subtracting 2x from both sides. 2x minus 2x is 0, leaving 10 all by itself. 2x minus 2x is also 0, leaving 10 all by itself. My variables disappeared, but this time I have a true statement because 10 and 10 are equal, which means all real numbers, which means that x can be anything. Which also kind of makes sense because here I have 2x's and 2x's, and on both sides I'm adding 10. So no matter what x is, this equation will also be balanced. It's really important with these type of equations that you balance your variables before trying to balance your numbers. Try examples 5 through 8. Pause the video, press play when you're ready to check your answers. Be sure to say what the variable can be by either saying no solution or all real numbers if your variable disappears. If your variable gets isolated, you've also accomplished your goal. So before you leave to submit, please just make sure that your solutions match, and if something doesn't match, fast forward to the part to look at where you went wrong. I would especially focus on examples 7 and 8, as these have some tricks to them. Now for example 5, I've got 5x minus 6 equals 5x minus 5. I started by distributing. Notice I didn't switch the order. The x term comes first, and then constant term comes second. Then I subtracted my variables to get my variables together, leaving me with negative 6 equals negative 5. Since my variable is gone, I need to expand on this to say what it can be, and since negative 6 and negative 5 are not equal, that would mean no solution. On example 6, I started by distributing to get 12x plus 8 equals 12x plus 8. I then got my variable terms together by subtracting 12x, leaving 8 equals 8, and since these two numbers are the same and the variable is gone, that's going to mean all real numbers, which means x can be anything. Here's an important one to take a look at. When you distribute, you're going to get 12x plus 18 equals 18x plus 18. This is one where it's really important to make sure that you're balancing your variables before balancing your numbers. I bet if you don't have this answer, you probably minused 18 before you minused 12x. So take a look at the order which you did things. When I minus 12x from both sides, I get 18 equals 6x plus 18. We've actually seen a similar problem before. I'm now going to go in reverse PEMDAS by getting rid of my plus 18 by subtracting it from both sides. The key here is that my equal sign cannot move at all, and 18 minus 18 is a number. That number just happens to be 0. I still need to get x by itself by dividing by 6, and 0 divided by 6 is 0. Notice I did not say no solution or all real numbers, because no solution means I don't get to open any doors, and I am opening a door. I'm opening door number 0. And I'm not saying all real numbers because I'm not opening all the doors. I'm only opening one door. It happens to be door number 0. See how in examples 5, 6, and 8 there is no variable? Here in example 7, I have the variable by itself. So I actually got the expectation of what I expected to happen, the expected behavior, which is I arrived at one solution. On example 8, negative 3 times 2x is negative 6x. Negative 3 times, be careful here, negative 7 is a positive 21. So just double check that. 6 times 4 is 24, minus 6 times x would be 6x. We would then add 6x to both sides because negative 6x plus 6x is 0, and it would also cancel on this side, leaving us with 21 equals 24. My variable is gone. Those two numbers are not equal, therefore my answer is no solution. Be careful, if you had this as a negative 21, you're probably still going to get no solution, but you would have had a precision error along the way.